So there are many, many ways to study the brain. We can use all kinds of non-invasive techniques to look at activity in the brain. You can look at electrical activity in the brain using electroencephalogram or magnetoencephalogram. Both of these are looking at electrical activity, not in single neurons, but in groups of neurons within an area. So you can look at sort of correlations between activity in one area of the brain and another area of the brain as someone's doing certain tasks, and look at connectivity based on which areas are firing at similar times when an individual is doing certain tasks. We can also record brainwaves. So we've got actually 5 brainwaves. Your book doesn't talk about gamma, but your lowest brainwaves are delta waves. And then you can measure theta, then you have alpha, beta, and gamma. And while I have gone over them in the notes quite extensively, including sort of the cutoffs of the wavelengths, or I would not take that too literally because different researchers, there's some window, different researchers will put some of these wavelengths at slightly different frequencies, or I should say frequencies, slightly different frequencies depending on whom you read. But in general, delta waves are 0 to 4 hertz, and then theta waves are 0 to 8, alpha waves are 8 to 12, beta, anything above 12 to 20 or even 40, and then gamma, anything above that, anything above 40. So there are different areas. Some people will say alpha waves go to 14. But suffice it to say, I'm not going to harp on that. There are 2 major waveforms that people are very familiar with, one of which are the alpha waves. And these you see in very relaxed people with their eyes closed. So people who are relaxed, they're in a kind of a mellow state, if you will. And then we have beta waves, which are usually seen when someone's concentrating, when they're doing a task and they're doing something and they're concentrating on it and they're not just relaxing, but they're thinking about a very specific thing and performing a specific function. We have our delta waves, which are very low frequency. These are our 0 to 4. Some people put them at 0.5 to 3.5 or 4 hertz. It's not that important, but these are seen in deep sleep in the entire population. They are seen in children, wake children, from ages 1 to 12 or 0 to 12. After 12, if you start seeing a lot of delta activity in adults, this could be a sign of pathology. We see theta waves. Theta waves are sometimes associated with meditation. They're sometimes associated with frustration. In adults, a lot of times we see if there's a lot of theta activity, that can be associated with pathology, like maybe tumors. But theta waves are seen in normal adults in certain circumstances. Then we have our gamma waves. These are higher frequency waves. And these waves are associated with linking ideas together and insights. So gamma waves have been studied more recently, in more recent times. And they're of interest to researchers who want to see how people achieve certain insights or how they link together certain ideas. All right. So this just explains everything that I said. Then you can see several slides here that show sort of what they look like. Here are alpha waves, and here are beta waves. And then they show you some theta waves, and then below that they show you some delta waves. And these are very low frequency waves, deep sleep typically. If you see them in adults, if you see a lot of this activity in adults who are awake, it's usually typical of a pathology. That's something that might be useful to know and is certainly useful for clinical applications. All right, so we've talked a little bit about neural activity, and we've shown some of these waveforms here, which are basically synchronizations of neural activity where you have multiple neurons within an area all firing or sending action potentials at about the same time. So what we have, if there's an abnormality in this, is we can have a seizure. And a seizure is an uncontrolled firing of action potentials. And this is usually, you could consider this an electrical storm in the brain. So this is uncontrolled, this is meaningless neural firing. So if you think of action potentials, as we've seen them, single action potentials, if you think of lots of action potentials as a code, as they're encoding information. Now imagine that if any of you have ever seen, for example, Morse code, when people are flipping the spotlights, for example, if you've ever seen any of the submarine movies where the submarines are communicating with one another, like Hunt for Red October, and they're flipping the lights and dots and dash patterns, and you can do this with sound as well. And you can have patterns of dots and dashes that represent a code. And that code means something. There are letters encoded in it. And you can sort of make the analogy that action potentials are doing something similar. There's a code in the information in the pattern that they convey. Now, if you just flipped all the lights on and left them on, or made this huge, horrendous, loud sound and it just blared on for, a long time, there's no information being conveyed. Imagine, for example, a symphony orchestra playing, and all the instruments are playing certain things, and they're playing a piece, and it's recognizable, and it conveys information, and you recognize that piece of music. Now imagine everybody in the orchestra just playing something random as loud as they can, not making any sense whatsoever. That's sort of like a seizure. So this is where you would have an inability to convey information. It's pathological, and it often causes excitotoxicity. That means that the neurons are so overstimulated that eventually they die from overactivity. So seizures can be quite damaging in the long run. And people who have epilepsy, they definitely don't want to continue having seizures. So that's why medication is given to epileptics, and a lot of attention is given to preventing seizures. And seizures are basically a synchronization of activity where all the neurons all at once just start firing as fast as they can. You can think of as an electrical storm in the brain. And it causes everything from movement disorders, disruptive speech, to full-blown tonic-clonic grand mal seizures where the person is just convulsing uncontrollably. And they usually have no memory of what happened after it happened because there was no meaningful information that was generated anywhere within the brain. All right, so basically, one of the reasons that people are interested in, especially clinicians, monitoring this brain activity is because these things are EEG traces, and they can tell you a little bit about activity in what the person's doing. For example, this person is basically sitting there with eyes closed and just relaxing. This person is probably concentrating on something. This person is probably in deep sleep or might have some kind of disorder. And if you look at patterns of activity across the brain, you can sort of garner an idea of what the person might be focused on, what they're doing, how awake they are, and these kinds of things. Now, people who are monitored for epilepsy, who come into the epilepsy unit, they will have these EEGs and they will have a montage of electrodes placed all around their heads. And when seizure activity is generated, what you get is this basically off the chart, very sharp, fast spiking activity. And this is the ictal period when the person is having the seizure. And there's no such of this nice, pretty waveforms here. The thing just looks like it went off the charts. Very fast activity, very high amplitude activity, and it's a complete disruption of any signal. So this is why EEG is important from a clinical setting. And it's also useful for looking at pathologies, any disruption in brain activity. But also scientists and researchers are interested in looking at this type of activity to give insights into how people think, how they learn, and how the brain is interconnected, and how ensembles of neurons in one area of the brain are communicating with groups of neurons in another area of the brain. All right, that brings us finally to our cranial nerves. Remember that we have 12 pairs of cranial nerves. And cranial nerves are things from the periphery. They're not part of the central nervous system. They're part of the peripheral nervous system that attach to the brain in some area. We have sensory nerves that bring sensory information to the brain. We have special sensory nerves, which would be things for like vision, olfaction, auditory and balance, gustation, that's taste. These are the special senses. These are the senses that reside in the head and are specific to one modality. And so a lot of the cranial nerves, a lot of the cranial nerves are dedicated to these special senses. Then we have motor nerves, which, for example, in the control of the eyes, we have three motor nerves that are cranial nerves that control eye movements. And we'll talk about those. That would be the ocular motor, the trochlear, and the abducens. We'll talk about them when we get a little bit further into the chapter, but those I will expect you to know. Then we have mixed nerves, which have both sensory information coming into them and motor commands leaving them. All right, so cranial nerves basically are numbered 1 through 12, and they are CN, Roman numeral, whichever they are. And so they can be identified by their primary function. For example, cranial nerve 1 is the olfactory nerve. It's also called the olfactory nerve because it brings information about smell. And also they can have, for example, this accessory nerve used to be called the spinal accessory nerve because it had some connections on the spine as well. So the vagus nerve, for example, means the wandering nerve, and it has a lot of control over visceral organs. And we'll talk about that in just a little bit, but first we'll show a few of them. This is the olfactory bulb. This is where the olfactory nerve or cranial nerve 1 terminates, and cranial nerve 1 is actually located in the epithelia of your nose and your nasal passages. And so this is what's going to bring information about smell. The cranial nerves, actually cranial nerve 1, are a collection of nerves that all have their axons coming up through the cribriform plate of the ethmoid bone. That's what that perforation is there for. So the perforations on either side of the crista galli, those perforations in the cribriform plate are for the olfactory nerve. The olfactory nerve then synapses on the olfactory bulb, which carries information via the olfactory tract into the olfactory cortex. Then we have our optic nerve. Here it's cut. You've seen it before. And it's what attaches to the eye. It brings information from the retina, which is a sheet of sensory neurons, and it's going to react to light. And then that information will be transmitted via the optic nerve and will eventually end up in the lateral geniculate nucleus of the thalamus. Remember, we have our optic nerve. It's going to cross at the optic chiasm, and then it's going to send information to the lateral geniculate nucleus of the thalamus via the optic tract. And the thalamus, you can't see it here, but then the thalamus is going to relay that information back to the visual cortex via the optic radiations. So here's our olfactory nerve. It brings information about smell, starts in the olfactory epithelium, goes up through the cribriform plate of the ethmoid bone, and then synapses on the olfactory bulbs. That's an important one to know. I would know that one. The next one would be, oh, here's a picture of it. Here's our olfactory nerve. Here it comes up through the cribriform plate, synapsing on the olfactory bulb. All right, so the next one that's important is the optic nerve. That's the one we've already seen, coming from the retina of the eye. We'll just go down straight to the picture. Optic nerve, optic chiasm, optic tract, lateral geniculate nucleus of the thalamus, optic radiations to the visual cortex. All right, now the oculomotor nerve is going to move the eyes. And this is very important because it's one of 3 of the cranial nerves that move the eyes. And it controls 4 of the 6 nerves that move the eye, and also controls the ciliary body and the thing that changes the iris and changes the lens of your eye too. So actually, I'm not sure about the iris. I have to look that up. But it does change the shape of the lens in your eye. And the oculomotor nerve is one of the major cranial nerves that move your eyes. Then we have the trochlear nerve, which also moves the eyes. And it operates on a muscle called the superior oblique, which is, if you look at it, it's on the top upper surface, the superior surface of the eye, and it goes through a connective tissue sling that acts as a pulley. And as we've seen before, the word trochlea means pulley. So the trochlear nerve activates the superior oblique, which really acts as though it's on a pulley. And so that's the name of the nerve. And we have the abducens nerve, which is nerve 6. So we jump from nerve 4, the trochlear nerve, to 6 because I am going over all the ones that control eye movements. And the abducens nerve is basically going to control the lateral rectus muscle of the eye, which is going to abduct the eye outward. So abduction is to take away something. So if you abduct a body part, you're moving it away from the midline. So if you abduct your eyes, you are looking laterally away from the midline. All right, so yeah, oculomotor nerve, it says right here. It operates 4 of these muscles of the eye, and it also operates the muscles of the eyelid. So I think it also operates the intrinsic eye muscles. It doesn't say much more than that here. Anyway, so here is our optic nerve, and then you can see here's your oculomotor nerve. You can see it attaching to a lot of these muscles here, the 4 of the 6. Here is your trochlear nerve operating this superior oblique, and look how it's slung through this connective tissue pulley called the trochlea, hence the name. And then you have the lateral rectus, which is not shown here. It's cut, and that would be your abducens nerve. Here it is, because I've cut and reflected it. So here's your lateral rectus muscle cut, and here's the abducens nerve that's innervating that. So those are the 3 muscles of the eyes. The one I skipped was the trigeminal nerve, which is 5, which basically is a sensory and motor nerve to the face. This is basically all you need to know about it. It has 3 divisions. It has the ophthalmic, the maxillary, and the mandibular division. And each one of those is going to innervate part of the face. And there's a nice picture of it in your book. I'm not going to expect you to know too much more than that. So here's your trigeminal nerve. Here's your ophthalmic branch up here. Here's your maxillary branch, and here's your mandibular branch, as they're named for where they go, obviously. All right, so then we have the facial nerve, which also is mixed sensory and motor to the face. Interestingly, it receives sensation from the anterior 2/3 of the tongue. So this is something that might be interesting to know. It receives information from the anterior 2/3 of the tongue, as well as other areas of the face. All right. So this is sort of what the facial nerve looks like. I'm not going to make you know all the details of it. Then we have a very important nerve. This is nerve number 8. This is the vestibulocochlear nerve. This is a special sensory nerve that's going to bring information about hearing, sound, from the ears to the brain, to the auditory cortex, where it's eventually going to end up. But also it brings balance information, because remember, the ear has the inner ear, which has the organs for sense of balance in there as well, and that's the vestibule of the ear, and we'll see that more in the special senses. So the vestibular cochlear nerve, nerve 8, cranial nerve 8, brings information about hearing and balance. All right, let's see what else. Here it is. Here is the vestibular branch, bringing information from this structure here, which is going to be conveying information about balance. And then this is the cochlear nerve, and cochlea means like snail shell, and you can see this thing is kind of snail shell look shaped. And they've cut out little sections of it so you can see the connections of this cochlear nerve all along this cochlea. And they come together into the vestibular cochlear nerve here. All right. Glossopharyngeal nerve, as the name implies, glosso has something to do with the tongue. Pharynx has something to do with the neck. So it's a mixed sensory and motor neuron to the head and neck. I'm not going to make you know much more than that. That's number 9. So number 10 is the vagus nerve. And vagus nerve is a very important nerve, and I will expect you to know it because it's called wandering nerve. Vagus means wandering. It's both mixed sensory and motor, but it is going to innervate the organs of the abdominopelvic and thoracic cavities. So this is very important. The vagus nerve is one you need to know, and we'll study it in more detail when we get into the autonomic nervous system, and we'll find it's a very important nerve in the parasympathetic division of the autonomic nervous system. All right, so then after the cranial nerve 10, which is the vagus nerve, here you can see some of the stuff it innervates. We have the accessory nerve. This is going to have motor function, innervate motor muscles of the back and neck, like the trapezius, and it's called the accessory nerve because, well, it used to be called the spinal accessory nerve, not anymore. But it's basically going to innervate the muscles of the neck and the upper back. All right, so finally, the last one is the hypoglossal nerve, and glosso, there again, glossal has to do with the tongue, and it is primarily motor movement to the tongue, and also, let's see, yeah, motor movements of the tongue. And then here's just all of these slides just show where you can find them. I'm not going to make you identify each one, but you probably do remember from lecture that 8 borders the pons and the medulla oblongata, that 8 through 10, or sorry, 8 through 12 come off the medulla oblongata, 5 through 8 come off the pons, and all the other ones come off above that. So that is where we will stop. This concludes the lecture on the brain.